Welcome to a quiet journey to the edge of our solar system, a voyage into the profound silence, where sunlight itself grows faint, and the solar wind finally surrenders to the gentle pressure of the galaxy. Voyager 1 is more than a spacecraft. It is a piece of us, our questions, our curiosity, our daring, sailing endlessly into the unknown. It has become our ambassador to the cosmos, a tiny spark of human wonder set adrift in the vast night. Tonight, we drift into a question that is not about what we can see, but about what we can hear in the whispers of the cosmic void. How do we know, with such certainty, that a small, silent spacecraft, a speck of metal and circuitry, launched over 4 decades ago, has truly crossed the invisible threshold into the space between the stars? How can we be sure that Voyager 1 has entered interstellar space when it is so far away that it has long since vanished from our most powerful telescopes, becoming a faint, distant memory against the backdrop of infinity? Before we begin this cosmic voyage, take a moment to settle in and tell me, where are you joining in from, and what time is it wherever you are? Find a comfortable position and allow your mind to relax. Let the day's concerns drift away, replaced by the slow, expansive thoughts of deep space and gentle discovery. And as you listen, we'd love to know where in the world you're listening from and what the night is like outside your window. Feel free to share in the comments, a quiet testament to our small, connected community of cosmic dreamers. Now take a deep, slow breath and let us embark on this journey together. A journey not of frantic excitement, but of calm, methodical, and profound understanding. To comprehend the journey of Voyager, we must first understand the nature of the ocean it now sails. Interstellar space. The words themselves evoke a sense of immense, quiet emptiness, a vast and seemingly infinite expanse that exists between the stellar islands of our galaxy. For most of human history, this realm was purely theoretical, a concept discussed by astronomers and dreamers, a canvas for the imagination. It was understood to be there, beyond the planets, but its properties, its boundaries, its very substance were mysteries waiting to be unraveled by a messenger brave enough to travel there. Our solar system, our familiar cosmic neighborhood, is not merely a collection of planets orbiting a star in the emptiness. It is a dynamic structure, a bubble carved out by the sun itself. The sun is not a quiet, passive ball of light. It is a roiling, energetic furnace, constantly exhaling a stream of charged particles, a superheated plasma that flows outward in all directions. This perpetual solar wind races away from the sun at incredible speeds, 1,000,000 miles per hour, carrying with it the sun's own magnetic field, stretching it and pulling it into a vast, invisible structure that envelops everything within its grasp. This bubble of solar influence, this extended atmosphere of our star, is known as the heliosphere. It is our home in a galactic sense, a protective cocoon that extends far beyond the orbit of the outermost planets. Within the heliosphere, the environment is dominated by the sun. The particles we encounter are mostly from the sun. The magnetic fields we can detect are shaped by the sun. It is a realm defined by its central star. And like any bubble, it must have an edge, a boundary, where the internal pressure of the solar wind can no longer push outward against the external pressure of what lies beyond. And what lies beyond the heliosphere is the true galaxy, the interstellar medium. This is not a perfect vacuum, though it is emptier than any vacuum we can create on Earth. It is a sparse, thin soup of material. Here, the particles are not from our sun, but are the remnants of ancient stellar explosions, the gentle ejecta of long-dead stars that have enriched the galaxy over billions of years. These particles are drifting, cool, and quiet. And permeating the space is the magnetic field of the galaxy itself, a faint but immense web of magnetism that guides the motion of cosmic rays and shapes the structure of the cosmos on the grandest scales. The boundary between these two realms, the hot, high-pressure bubble of the heliosphere and the cool, dense pressure of the interstellar medium, is the frontier we sought to find. This boundary is not a sharp, solid wall, but a complex and layered region of interaction, a place of quiet turbulence and fundamental change, a place where the sun's influence wanes and the galaxy's influence begins to dominate. For Voyager 1 to reach interstellar space, it had to first journey through the outermost layers of the heliosphere, navigate this complex boundary zone, and finally emerge into a region where the particles and fields around it were unequivocally from the galaxy beyond our star. This was the grand, silent quest of the Voyager mission. Not just to visit the outer planets, which it did with breathtaking elegance, but to continue on, to become a physical probe of this final frontier, to feel the edge of the solar bubble and report back on what it found there. And it had to do this not with pictures, for there is nothing to see, but with feelings, with instruments designed to listen, to feel the solar wind, to count the particles, to sense the magnetic fields. Its mission was to become a blind explorer, using its other senses to map an invisible world. Its eyes had long since shut down, its cameras powered off after their final planetary portraits. But its ears, its sensitive fingers, remained active, listening intently to the whispers of the cosmos, waiting for the moment the whisper would change and tell us we had arrived somewhere new. To truly appreciate the silent message Voyager 1 sent back from the edge, we must first understand the messenger itself, its design, its instruments, its very nature as a physical object on an impossible journey. The Voyager probes, twins Voyager 1 and 2, were conceived in an era of bold exploration, their mission parameters ambitious yet precise. A grand tour of the outer planets leveraging a rare planetary alignment that happens only once every 17.6 years. They were built to be planetary photographers, to capture the details of Jupiter's swirling storms, Saturn's intricate rings, the strange icy moons that hinted at subsurface oceans. But even in their design, there was a whisper of a more profound, more distant future. A hope that they might survive long enough to journey into the unknown darkness beyond. The spacecraft themselves are marvels of engineering, yet their design is elegantly simple from a distance. Each is built around a 10-sided bus, a central structure housing most of the electronics, like a quiet, metallic heart. From this core, various appendages extend, each with a specific, silent purpose. A large, parabolic, high-gain antenna, 3.7 meters across, acts as its singular ear and mouth, its only means of communication with the pale blue dot it left behind. This dish is perpetually pointed towards Earth, a silent gesture of connection across billions of miles. To power its systems in the dim sunlight so far from home, Voyager carries 3 radioisotope thermoelectric generators, RTGs. These are not solar panels, they are nuclear batteries, fueled by the slow, steady, and relentless radioactive decay of plutonium-238. This decay generates heat, and that heat is elegantly converted into electricity, providing a faint but unwavering trickle of power, a few hundred watts, just enough to keep its systems warm and its instruments listening in the profound cold of space. But its true soul, for our story, lies not in its structure or its power source, but in its senses, its instruments. While its famous cameras have long been deactivated to conserve power, the suite of fields and particles instruments remain its fingertips, its way of feeling the environment through which it travels. These are the tools that would ultimately tell the story of its crossing. The low-energy charged particle instrument, designed to measure the fluxes of ions and electrons, the cosmic ray subsystem, tuned to detect the high-energy atomic nuclei that race through the galaxy, the magnetometer, perhaps the most crucial sense of all, consisting of two sensors on a long 13-meter boom placed far away from the magnetic interference of the spacecraft's own body. This instrument feels the strength and direction of magnetic fields, the invisible architecture of space itself, and the plasma wave system, which doesn't measure plasma directly, but listens to the oscillations of electrons in the plasma, a kind of microphone that hears the roar of the solar wind and the hiss of the interstellar medium. Its journey was a slow, quiet crescendo of discovery. After its triumphant planetary encounters, the volcanic plumes of Io, the complex dynamics of Saturn's rings, Voyager 1's path was bent by Saturn's gravity on a trajectory that took it high above the plane of the solar system, a lonely northward climb out of the orbital flatland where the planets reside. Meanwhile, its twin, Voyager 2, was directed on a slower, lower path that would eventually take it past Uranus and Neptune, a path that would also lead it toward the southern boundary of the heliosphere. For years after these encounters, the Voyagers entered a phase often called the Voyager interstellar mission, a long, quiet cruise through the outer darkness. During this time, their data was no longer punctuated by spectacular images of new worlds, but by the slow, patient, and meticulous recording of their environment. The steady stream of particles, the constant reading of the magnetic field. It was a monotonous, yet profound dataset, a baseline of the heliosphere's character. For decades, the data was consistent, a testament to the stability of the solar wind's outflow. The particles detected were predominantly from the sun, their energy and direction predictable. The magnetic field, though weakening with distance, still clearly bore the signature of the sun's influence, its orientation largely as expected. It was a long, quiet sail on a steady current. But scientists knew this could not last forever. The pressure of the interstellar medium outside was constant, and as the solar wind expanded, it would inevitably thin out, its pressure decreasing until it could no longer hold back the galactic environment. The question was not if Voyager would encounter this boundary, but when, and what would the transition look like? Would it be a sudden wall, a single definitive crossing, or would it be a gradual, messy region of interaction, a slow blending of two cosmic climates? The spacecraft continued its silent outward drift, its radio signals growing ever fainter, taking longer and longer to travel back to Earth. Each day, it set a new record for distance from home, a record that would never be broken by any other human-made object for generations to come. It was a journey into the unknown, not of geography, but of environment. A journey to find the edge of the sun's empire by feeling the subtle changes in the cosmic weather. And we waited, listening patiently to its whisper, knowing that one day that whisper would change its tune, telling a new story written in the language of particles and magnetic fields. The long, quiet vigil had begun, a search for an invisible finish line in the dark. The journey of Voyager 1 through the profound quiet of the outer solar system was a testament to patience, a decades-long vigil where change was measured not in days or months, but in years. For a long time, the data streaming back to Earth was a study in comforting constancy, a predictable and steady record of the sun's enduring influence. The spacecraft was sailing on the solar wind, that perpetual and invisible river of charged particles flowing outward from the sun at tremendous speeds, 1,000,000 miles per hour. This wind, composed mostly of protons and electrons, carried with it the sun's magnetic field, stretching it and pulling it into a vast, spiraling structure that defined the entire volume of the heliosphere. Within this bubble, the environment was entirely dominated by our star. The particles were solar. The magnetic field was solar. It was a known world, and Voyager's instruments reported back its familiar properties with a reassuring regularity. The magnetometer readings showed a field that, while weakening predictably with distance, maintained a clear connection to the sun's rotational plane and polarity. The particle detectors registered the familiar signatures of the solar wind, a constant stream that had become the background hum of Voyager's existence. Yet, the laws of physics dictated that this could not last forever. Just as a river must eventually slow and spread as it meets the resisting mass of the ocean, the solar wind must eventually terminate. It flows outward until its pressure is no longer sufficient to push back against the combined pressures of the interstellar medium, the gas, dust, and magnetic fields that fill the space between the stars. Theorists had long predicted a boundary where this dramatic slowdown would occur, a region they called the termination shock. This would not be the final edge of the solar system, but rather the beginning of its outer boundary layer. At the termination shock, the supersonic solar wind would make a sudden, chaotic transition to subsonic flow. The particles would be compressed, heated, and accelerated in this turbulent region, creating a detectable signature, a clear indicator that the spacecraft was entering the sun's final frontier. The wait for this signal was an exercise in scientific anticipation. Then, in December of 2004, when Voyager 1 was approximately 94 astronomical units from the sun, a distance so vast that light itself takes over 13 hours to traverse it, the data began to tell a new, more complex story. The low-energy charged particle instrument registered a significant and sudden increase in the intensity of energetic particles. These were not the calm, steady particles of the solar wind. These were particles that had been jolted to higher energies, a telltale sign of a shock wave. Simultaneously, the plasma wave instrument detected a pronounced increase in the pressure of the plasma surrounding the spacecraft. Most critically, measurements of the solar wind's speed showed a dramatic and unmistakable drop. The outward velocity, which had been steady for so long, plummeted by more than a factor of 4. The river had met the sea. After a journey of over 27 years, Voyager 1 had crossed the termination shock. It had passed from the calm, supersonic flow of the solar wind into the turbulent and compressed region known as the heliosheath. The heliosheath is the sun's final atmospheric layer, a vast and churning estuary where the now subsonic solar wind is heated, compressed, and diverted, flowing sideways along the inner boundary of the heliopause before eventually turning tail and flowing down the tail of the heliosphere. It is a region of complex and dynamic interaction where the pressure from within battles the pressure from without. Crossing the termination shock was a monumental milestone, a validation of theoretical models and a first touch of the solar system's outer skin. But it was emphatically not the final goal. It was the confirmation that the final goal lay ahead. Voyager was now within the gateway, but it had not yet stepped through the door. The spacecraft began its long sail through this mysterious region, and scientists settled in for what they estimated could be a journey of several more years before it reached the true boundary, the heliopause. This voyage through the heliosheath was itself a period of profound discovery, revealing a far more complex and dynamic environment than many had anticipated. The pressure of the local interstellar medium was found to be stronger than some models predicted, likely from the magnetic field pressure, which compressed the entire heliosphere, making the heliosheath thinner and causing the termination shock to be encountered sooner than expected. The magnetic field within the heliosheath became increasingly turbulent, its direction fluctuating wildly as it was buffeted by external forces, a sign that the spacecraft was getting closer to the realm where the galactic magnetic field would dominate. Most intriguingly, the particle data began to show a slow but steady shift in composition. The intensity of the solar wind particles continued to decrease, becoming ever rarer and lethargic. But at the same time, a new background signal began to emerge, a faint but persistent whisper growing slowly louder against the fading solar hum. This was the signature of galactic cosmic rays. High-energy particles accelerated from distant supernova and other violent events across the galaxy. Their numbers were slowly, inexorably rising. It was as if Voyager was a submarine and the pressure hull was beginning to groan, the sounds of the deep ocean outside becoming ever more audible. The door to the galaxy was not yet open, but the draft from under it was growing stronger, a promise of the immense space that lay just beyond. The passage of Voyager 1 through the heliosheath was not a simple, linear journey toward a well-defined border. Instead, it became a slow, meandering exploration of a complex and dynamic frontier zone, a region where the familiar laws of the solar system began to fray at the edges, giving way to the subtle and unknown influences of the galaxy at large. This phase of the mission, lasting years, was a profound exercise in scientific patience, a lesson in interpreting ambiguity and waiting for the universe to reveal its secrets on its own immense timescale. The heliosheath was revealed to be not a placid pool of stagnating solar wind, but a realm of intricate structure and unexpected phenomena. A cosmic estuary where the tides of two different stellar environments met and mingled in slow motion. For a long period after crossing the termination shock in 2004, the data from Voyager settled into a new, though fluctuating, normal. The solar wind particles were now subsonic, their energy diminished, their flow often turbulent. The magnetic field, while still fundamentally solar in origin, began to show signs of stress, its direction becoming more variable as it felt the increasing pressure from the interstellar medium outside. It was an environment in transition, and Voyager was its meticulous cartographer, mapping an invisible geography of forces and particles. The scientists on Earth analyzed every blip and change in the data stream, looking for patterns, for clues that would indicate the proximity of the true boundary, the heliopause. The models suggested it could still be years away, but the models were based on incomplete knowledge. Voyager was the first and only probe to send back data from this realm, and it was rewriting the textbooks in real time. Then, beginning in 2010, the spacecraft began to encounter something entirely new and unpredicted, what scientists came to call cosmic ray highways, or magnetic flux tubes. These were periods, sometimes lasting for months, where the environment around Voyager would undergo a dramatic and puzzling transformation. The most striking change was in the particle counts. The low-energy particles that had originated from the sun would suddenly and precipitously drop away, their numbers vanishing to almost nothing. It was as if a vast, invisible vacuum cleaner had suddenly whisked them all away. Simultaneously, and just as dramatically, the high-energy cosmic rays that originated from far beyond the solar system, from distant supernova explosions and other violent galactic events, would surge to levels never before seen by the spacecraft. These events were like nothing encountered before. They were not a gradual blending of environments, but a sharp and startling switch. It was as if Voyager had suddenly found a temporary opening, a hidden passageway that connected it directly to the galaxy beyond, allowing interstellar particles to pour in unimpeded, while the solar particles were flushed out. The leading theory to explain these phenomena involved magnetic reconnection. At these immense distances, the magnetic field lines emanating from the sun become stretched and stressed to their breaking point. The theory suggested that these stressed solar magnetic field lines could occasionally snap and reconnect with the magnetic field lines of the interstellar medium. This would create a temporary magnetic highway, a direct pipeline that connected the inside of the heliosphere with the outside galaxy. For a brief period, particles could travel freely along this highway, explaining the sudden influx of cosmic rays and the exodus of solar particles. For the mission scientists, these events were periods of intense excitement and fascination. Each event was a precious data set, a sneak preview of the interstellar environment that lay in wait. They provided crucial clues about the nature of the magnetic field just beyond the heliopause and the energy spectrum of the galactic cosmic rays. Yet they were also periods of slight frustration. Each time one of these cosmic ray highways appeared, the team would wonder, is this it? Has the heliopause finally been breached? But each time, after weeks or months, the connection would break. The solar magnetic field would reassert itself, the solar particles would trickle back, and the cosmic ray counts would subside to their previous elevated but not dominant levels. Voyager would find itself back in the familiar, if strange, environment of the heliosheath. It was like approaching a door, seeing it crack open to reveal the brilliant light from the other side, only to have it swing shut again before one could step through. These repeated forays to the very edge of the solar influence were critical for another reason. They helped scientists refine their understanding of what the final, irreversible crossing would look like. The temporary nature of the cosmic ray highways confirmed that a single dramatic particle event alone would not be sufficient proof of interstellar space. The true crossing would require a permanent change. The particle data would have to show a definitive and unwavering transition, the permanent disappearance of solar particles, and the permanent establishment of a new, higher baseline for galactic cosmic rays. But even more importantly, the theorists emphasized that the most definitive signature would be a change in the magnetic field. The solar magnetic field, even when stressed and turbulent, had a certain character and orientation. The interstellar magnetic field, shaped by the galaxy's dynamics and the local fluff of interstellar cloud through which the sun is moving, was predicted to be different, to have a different strength and a fundamentally different direction. When Voyager finally crossed the heliopause, its magnetometer would record a permanent shift in the magnetic field. This change, combined with the permanent particle shift, would be the undeniable proof. The magnetic field was the ultimate arbiter, the final judge that would confirm the spacecraft had truly left the sun's magnetic embrace and entered the magnetic realm of the galaxy. And so the long vigil continued. Voyager 1, a silent, patient machine, continued its outward drift, its instruments faithfully recording the ebb and flow of particles, the twists and turns of the magnetic field. Each data packet that arrived on Earth, after traveling for over 16 hours at the speed of light, was scrutinized for the telltale signs of the final transition. The cosmic ray highways had shown that the boundary was close, perhaps closer than anyone had dared hope. They had shown that the door was there and that it was opening, if only for brief moments. The question was no longer if, but when the door would open for good, allowing humanity's first emissary to the stars to finally step through into the interstellar void. The spacecraft was sailing through the final currents of the solar system's river, and the vast ocean of the galaxy was just ahead, its waves finally audible as a steady, rising whisper in the data. The year 2012 dawned, with Voyager 1 continuing its silent, unending drift through the outer reaches of the heliosheath. For months, it had been experiencing these strange and captivating magnetic highway events, each one a tantalizing glimpse of the galaxy beyond, each one followed by a return to the now familiar, though increasingly alien, environment of the sun's diminished influence. The data patterns had become a kind of rhythm, a slow, cosmic breathing where the door to interstellar space would crack open and then sigh shut again. But by the middle of that year, a subtle yet persistent change began to weave its way through the data stream. The rhythm was changing. The particle counts, which had previously swung dramatically between solar and galactic dominance during these events, began to behave differently. The dropouts of solar particles became more severe, and the surges of galactic cosmic rays not only reached higher peaks, but more importantly, did not fully recede when the event concluded. Each oscillation left a residual higher level of galactic particles, as if the tide of the galaxy was coming in, and each wave was washing a little farther up the solar shore, never fully retreating. This gradual, ratcheting increase was the first quiet hint that something fundamental was shifting. The temporary cracks in the heliospheric bubble were becoming wider, lasting longer, and perhaps were not fully sealing themselves shut. The background hum of the galaxy was becoming a permanent feature of the soundscape, growing steadily louder, while the melody of the sun was fading into a distant, fragmented echo. The scientists monitoring the data began to feel a heightened sense of anticipation. The spacecraft was now over 120 astronomical units from the sun, so far away that a single round-trip communication, a signal sent from Earth and a response received, took over 34 hours. Every command was considered with immense care, every byte of data precious. The team was listening for a symphony of changes, waiting for all the instruments to play the same new chord in perfect, permanent harmony. Then, in late July of 2012, Voyager entered another one of these particle events. The familiar signature appeared. Solar particles plummeted, cosmic rays surged. The team watched, expecting another temporary fluctuation. But this time, the solar particles did not return. Their numbers flatlined, vanishing to levels so low they were virtually undetectable. It was as if a great valve had been closed, finally shutting off the flow from the sun entirely. At the same time, the intensity of galactic cosmic rays surged and then stabilized, locking in at a new, significantly higher level. They did not subside. This was no longer a temporary highway. It was a fundamental and permanent shift in the particle population. The environment around Voyager 1 had, from the perspective of its particle detectors, become unequivocally interstellar. The first crucial piece of the puzzle had clicked decisively into place. The date was July 28, 2012. A quiet celebration rippled through the team, but it was a cautious one. This was powerful evidence, but based on years of experience with these events, they knew it could still, in theory, be another bizarre and extended fluctuation of the heliosheath. The gold standard, the definitive proof, still lay with the magnetometer. And so began a period of intense and patient waiting. The particle data was screaming that Voyager had crossed the boundary, But the magnetic field data was still whispering a different, more familiar story. The magnetometer readings showed that the strength of the magnetic field had increased significantly, which was expected at a boundary where plasma is compressed, but the direction of the field had not yet changed. It was still aligned roughly with the solar magnetic field. This was the conundrum. How could the particles be entirely galactic if the magnetic field was still solar? For over a month, the team pored over the data, analyzing and reanalyzing every nuance. They had expected the magnetic field shift to be simultaneous with the particle shift. The fact that it wasn't forced a profound reconsideration of the physics at the heliopause. Perhaps the boundary was not a sharp, textbook perfect wall, but a more nuanced and layered region. Perhaps the magnetic fields of the sun and the galaxy could, for a time, be aligned, preventing an immediate directional change. Or perhaps Voyager had crossed into a previously unknown heliosheath depletion region, or a magnetic barrier, a final layer of the sun's domain where the particles had been stripped away, but the magnetic field still held sway. This period was a testament to the scientific process, the careful, methodical, and sometimes frustrating work of reconciling data with theory. The team did not rush to announce a discovery. Instead, they gathered more data, debated interpretations, and developed new models to explain the apparent discrepancy. They commanded Voyager to perform a series of gentle rolls, a maneuver it hadn't executed in decades, to allow the magnetometer to better characterize the local magnetic field and ensure the readings were not being affected by some minute, undetected background field from the spacecraft itself. The rolls confirmed the initial data. The field was stronger, but its direction had not yet definitively flipped. Voyager was in a new place, a place no spacecraft had ever been, and it was revealing that this place was more complex and strange than anyone had dreamed. The particle evidence was overwhelming, but the magnetic proof, the final seal of approval, remained elusive. The spacecraft was hanging in a cosmic limbo, its instruments reporting from a realm that defied easy classification. The door had been pushed open, but had it fully stepped through? The answer lay in waiting just a little while longer, in allowing the silent traveler to drift just a little farther into the unknown, listening for the final, confirming whisper from its most sensitive fingertips. The late summer and early autumn of 2012 were a period of profound scientific suspense for the Voyager team. The spacecraft was sending back a deeply puzzling, almost contradictory set of readings. The particle data was unequivocal, the solar wind had vanished, and the environment was now dominated by a steady, intense flux of galactic cosmic rays. This was the signature they had been waiting for, the clear indicator that the sun's particle influence had ended. Yet, the magnetometer stubbornly refused to confirm the story. It reported a magnetic field that was stronger, as expected at a boundary layer where compression occurs, but its direction had not made the decisive, permanent shift that models predicted would accompany a crossing into the interstellar medium. The magnetic field still felt, for all intents and purposes, solar. It was as if Voyager had sailed into a new ocean, but found that the water, while now saltier and denser, was still flowing in the same direction as the river it had left behind. This discrepancy forced a period of intense reflection and reanalysis. The team had long established that a change in the magnetic field direction was the ultimate criterion for confirming the crossing. The particles could be fickle, as the magnetic highway events had shown, but the magnetic field was considered the bedrock truth of the local environment. Its persistence suggested one of two possibilities, each fascinating in its own right. The first, more cautious possibility was that Voyager had not yet crossed the heliopause, but had instead entered a previously unknown heliosheath depletion region, or a magnetic barrier, a final layer of the sun's domain where the particles had been effectively scoured away by the pressure of the interstellar medium, but the magnetic field still managed to hold its structure, like a ghostly outline of a room after the furniture has been removed. The second, more thrilling possibility was that Voyager had indeed crossed the heliopause, but that the local interstellar magnetic field was, by chance, aligned in a very similar direction to the solar magnetic field at that particular location. If this were true, the magnetometer would not detect a dramatic flip, but perhaps only a subtle, more nuanced change in field characteristics that would require incredibly sensitive analysis to detect. To resolve this, the team devised a gentle and elegant test. They commanded Voyager 1, a spacecraft built in the 1970s and now over 18 billion kilometers away, to perform a series of slow rolls. This was a maneuver not attempted in decades, a delicate ballet in the deep dark. The purpose was to allow the magnetometer, mounted on its long boom, to precisely characterize the ambient magnetic field from different angles. This would help the team on Earth determine if the field they were measuring was indeed the true interstellar field, or if it was still being influenced, and perhaps slightly twisted, by the lingering presence of the heliosphere. It was a testament to the exquisite design and durability of the spacecraft that it could still execute such a maneuver with precision after 35 years in space. For several days in September and October, Voyager slowly pirouetted, its magnetometer gathering a richer, more three-dimensional data set on the magnetic environment. The results of these rolls were crucial. They confirmed that the magnetic field being measured was indeed the ambient field, and not an artifact of the spacecraft. The field was real, it was strong, and it was persistent. But its direction remained puzzlingly familiar. During this period of analysis, another key measurement came into play, one that would ultimately break the deadlock and provide the missing proof: plasma density. The plasma wave instrument on Voyager was not designed to measure plasma density directly. Instead, it was like a sensitive microphone, listening to the oscillations of electrons in the surrounding plasma. However, these oscillations occur at a characteristic frequency that is directly proportional to the density of the plasma. A higher density of plasma produces a higher frequency of oscillation. It's akin to listening to the pitch of a ringing bell. The size and density of the bell determine the note it rings. For most of its journey, the PWS had been listening to the tenuous, high-pitched ring of the low-density solar wind plasma. But if Voyager had truly entered interstellar space, it should be surrounded by the cooler, denser plasma of the interstellar medium, which would produce a much lower, deeper note when stimulated. The challenge was that the plasma is typically too quiet to stimulate these oscillations. It needs a shock wave, a solar eruption, to make it ring. The team needed a cosmic event, a burst of energy from the sun that had left months earlier, racing out to Voyager's location at the speed of light, its arrival imminent, and its message holding the key to the mystery. The final, definitive proof of Voyager 1's crossing did not come from a single instrument reading a sudden change, but from a symphony of data, a convergence of evidence that unfolded over months. The particle data had spoken loudly and clearly in late July 2012, declaring the solar wind gone and the galaxy arrived. The magnetic field data, however, remained enigmatic. its persistent solar-like direction creating a scientific tension that required a new kind of key to unlock. That key was plasma density, and it would be provided not by a command from Earth, but by a tantrum from the sun that had occurred months earlier. The story of the confirmation is a beautiful example of cosmic serendipity and human ingenuity, a patient waiting for the universe to provide the exact clue needed to solve the mystery. The Plasma Wave Science Instrument, PWS, on Voyager 1 is essentially a highly sensitive radio receiver connected to two long antennas stretching out from the spacecraft's body. It was designed not to measure plasma directly, but to listen to the electron-plasma oscillations, the collective vibrations of electrons within the surrounding environment. The genius of this method lies in a fundamental physical relationship. The frequency of these oscillations is directly proportional to the square root of the plasma electron density. In simpler terms, the higher the density of the plasma, the higher the pitch of the oscillation it produces. It is precisely like striking a bell. A large, dense bell rings with a deep, low tone, while a small, less dense bell rings with a high, sharp tone. For decades, Voyager had been listening to the high, faint ping of the tenuous solar wind plasma. The interstellar medium, however, was predicted to be filled with a much denser, cooler plasma. If Voyager was truly there, the note of the plasma oscillations should have dropped to a significantly deeper, lower frequency. The challenge was that the plasma is typically quiet. It doesn't constantly ring. To make it oscillate and reveal its density, it needs to be stimulated by a shock wave, a pressure front that energizes the electrons and causes them to vibrate. These shocks can be generated by powerful events on the sun, such as coronal mass ejections, massive eruptions of solar material and magnetic field. These eruptions travel outward through the solar system, and if one were to reach Voyager's location, it would cause the local plasma to ring, and the PWS would record the tone. The frequency of that tone would directly reveal the density of the plasma surrounding the spacecraft. This was the measurement the team desperately needed. It was the missing piece that could break the logjam between the particle data and the magnetic field data. They were, in effect, waiting for a solar storm that had departed months before to travel the immense distance to Voyager and strike the interstellar bell. In March of 2012, the sun had obliged. A series of moderate coronal mass ejections had erupted from the sun's surface. These bubbles of magnetized plasma began their long journey outward, racing through the solar system at millions of miles per hour. The Voyager team, aware of these events, began a patient vigil. They calculated the approximate arrival time, knowing it would take months for the shock waves to traverse the billions of miles to Voyager's position. The wait was a quiet exercise in cosmic anticipation. Then, in April and May of 2013, nearly a full year after the initial particle change, and 9 months after the event itself had left the sun, the shock waves finally arrived. The PWS instrument began to detect something extraordinary. It picked up a series of faint, low-frequency oscillations. The team analyzed the data with immense care. The frequency of these oscillations was centered around 2.6 kilohertz. Plugging this number into the simple formula, they calculated the corresponding plasma density. The result was stunning. The density was measured to be approximately 0.08 electrons per cubic centimeter. This was more than 40 times denser than the plasma densities measured inside the heliosheath, and exactly what astrophysicists had predicted for the local interstellar medium. This was the sound of interstellar space. The deep, low hum was utterly different from the high-pitched ping of the solar wind. The sun's eruption had traveled all the way to Voyager, struck the plasma bell, and it had rung with the profound, deep tone of the galactic ocean. This measurement was the clincher. It provided the third independent line of evidence that corroborated the story told by the particles and finally explained the puzzle of the magnetic field. The reason the magnetic field direction had not changed dramatically was that, by chance, the direction of the local interstellar magnetic field was oriented very similarly to the solar magnetic field at that particular point of exit. The field had strengthened, as expected when compressed at a boundary, but its direction had only shifted subtly by a matter of degrees, a change that was only discernible with the most painstaking analysis once the plasma density had confirmed their location. The three lines of evidence, the disappearance of solar particles, the surge of galactic cosmic rays, and the detection of dense interstellar plasma, now formed an irrefutable triad. The verdict was in. Voyager 1 had crossed the heliopause. The announcement was made in a series of scientific papers in September 2013, but the official crossing date was set for August 25, 2012, the point at which the particle and plasma data showed the change had become permanent. After 35 years of travel, humanity had finally touched the interstellar medium. With the triumvirate of evidence now complete, the permanent vanishings of solar particles, the enduring dominance of galactic cosmic rays, and the profound low-frequency hum of dense interstellar plasma confirmed by the plasma wave instrument, the scientific community could state with unwavering certainty that Voyager 1 had crossed the heliopause. The date of August 25, 2012 was enshrined as the historic moment humanity's first interstellar envoy sailed beyond the final magnetic and particle boundary of the sun's influence. Yet this crossing was not an end, but a magnificent beginning. The door had swung open, and Voyager now found itself in an entirely new realm of study, the local interstellar medium. This environment, while now definitively galactic, was not a perfect, undisturbed void. It was a region shaped by its proximity to our solar bubble, a complex and dynamic zone of interaction where the echoes of the sun's presence could still be faintly detected, and where Voyager's instruments began to paint a picture of a universe far richer and more textured than previously imagined. The first major discovery in this new realm concerned the very nature of the magnetic field that had initially posed such a puzzle. The painstaking analysis, made possible once the plasma density confirmed their location, revealed that the magnetic field had indeed changed. While its direction had not performed the dramatic, obvious flip some models had predicted, it had shifted by a subtle but statistically significant amount. The slight change, combined with the measured increase in field strength, was the final magnetic proof. It confirmed that the field was now being dominated by the local interstellar magnetic field, and its orientation suggested it was being draped around the outer surface of the heliosphere, much like water flows around the bow of a ship. This draping effect helped explain the earlier confusion. Voyager had crossed the boundary at a point where the interstellar field was aligned in a somewhat similar direction, and the compression and draping at the heliopause had further influenced its characteristics. This was a profound lesson. The boundary between star systems and interstellar space is not a neat, clean line, but a messy, structured, and magnetically complex interface. Furthermore, Voyager's continued measurements began to reveal the sonic geography of this new frontier. The plasma wave instrument, having provided the key evidence for the crossing, now became a primary tool for mapping the interstellar environment. Over the following years, the Sun continued to occasionally send out coronal mass ejections. These powerful shock waves would travel through the heliosphere, cross the heliopause, and propagate into the interstellar medium. When they reached Voyager, now acting as a stationary buoy in the galactic ocean, they would cause the local plasma to ring once more. Each ringing event was a new measurement, and these measurements revealed something astonishing. The plasma density was increasing. As Voyager moved farther away from the heliopause and deeper into the interstellar medium, the density of the plasma around it steadily climbed. This was the first direct evidence that Voyager was moving through what astronomers call the interstellar cloud. The solar system is not moving through a uniform void. It is traveling through a specific region of slightly denser gas and dust, known as the local interstellar cloud. Voyager was now measuring the properties of this cloud directly, charting its gradient and structure for the very first time. Each new plasma oscillation event was like taking another core sample from this galactic environment, building a profile of our local galactic neighborhood. Simultaneously, the cosmic ray detectors were making their own startling discovery. While the overall levels of galactic cosmic rays had surged permanently after the crossing, the data showed a curious and unexpected anisotropy, a directionality to these particles. The cosmic rays were not arriving uniformly from all directions. Instead, they were streaming in along the magnetic field lines of the interstellar medium. This provided further independent confirmation of the new magnetic field orientation and showed how the galaxy's magnetic architecture channels these high-energy particles through space. It was a vivid demonstration that interstellar space is not a random and chaotic void, but a structured medium with currents and highways shaped by immense magnetic forces. Voyager was no longer just a traveler, it had become a weather station, reporting on the climate of the galaxy, measuring the magnetic breezes and particle rains that fill the space between the stars. Its continued journey, even after the monumental crossing, was yielding a continuous stream of first-time discoveries, each data packet refining our understanding of the cosmic ocean that cradles our star and its planets. The mission had achieved its primary goal, only to find that the road beyond it was even more fascinating, a path leading deeper into the mysteries of the galaxy itself. The confirmation of Voyager 1's interstellar crossing marked a monumental achievement, but it also opened a new and even more profound chapter in its mission, the exploration of the local interstellar medium itself. No longer was the spacecraft defined by what it had left behind, it was now defined by the new environment it was steadily mapping. This region, while free from the dominant particle flow of the Sun, is not a perfect vacuum nor a static, placid sea. It is a dynamic realm, a cosmic weather pattern shaped by the gentle pressure of the galaxy and the lingering faint echo of our star's presence. Voyager's instruments, still dutifully operational in the profound cold and silence, began to act as sensitive probes of this new territory, revealing its subtle textures and complex interactions in exquisite detail. The data returned was no longer about a boundary crossing, but about characterization, understanding the very fabric of the space between the stars. One of the most significant ongoing measurements came from the plasma wave instrument. The fortunate solar eruptions that had provided the key density measurement in 2013 demonstrated a new method for probing this environment. As the Sun continued its 11-year activity cycle, it periodically launched more coronal mass ejections into space. These immense clouds of magnetized plasma would travel outward for a year or more before reaching Voyager's location. Each time one of these shock waves arrived, it would energize the local interstellar plasma, causing it to oscillate. The PWS would detect these oscillations, and each event provided a new, precise measurement of the plasma density at Voyager's exact location. Over time, a fascinating trend emerged. The density was not constant. With each new measurement, the calculated density was slightly higher than the last. Voyager was moving deeper into what astronomers call the local interstellar cloud, a region of slightly denser gas and dust within the broader galactic environment. This was the first ever direct measurement of a gradient in the interstellar medium, a slow and steady increase in density as the spacecraft traveled further from the influence of the heliosphere and deeper into this local cloud. It was like measuring the increasing salinity of water as one sails farther from a river's mouth and into the open ocean. Simultaneously, the magnetometer continued its unending vigil, tracking the strength and direction of the interstellar magnetic field. The data revealed that this field was not perfectly uniform or smooth. It exhibited subtle fluctuations and variations, what scientists describe as turbulence. This interstellar turbulence is thought to be generated by the movement of the heliosphere itself through the cloud. As our solar system plows through this galactic material at a speed of about 52,000 miles per hour, it creates a kind of bow wave and a wake, disturbing the magnetic field lines and creating ripples and eddies in the magnetic fabric of space. Voyager, by measuring these tiny fluctuations, is effectively mapping the magnetic wake of our entire solar system. It is measuring the ghostly imprint that our star leaves on the galaxy as it travels on its long orbit around the Milky Way's center. This delicate magnetic mapping provides crucial insights into the pressure balance that defines the size and shape of our heliospheric bubble from the outside. The cosmic ray detectors also continued to provide surprises. While the overall level of galactic cosmic rays had stabilized at a new high baseline, the instruments detected a curious and persistent phenomenon, a faint trickle of particles that seemed to be leaking back into interstellar space from inside the heliosphere. These were anomalous cosmic rays, particles that had originated from the solar wind, been accelerated to high energies at the termination shock, and were now, somehow, finding a way to escape the solar system and diffuse out into the galaxy. Their presence around Voyager showed that the heliopause is not a perfectly sealed container. It is a semi-permeable membrane, allowing for a slow exchange of material between the solar system and the galaxy. This leakage is a two-way street. Just as these solar particles leak out, galactic material must also slowly filter in, a constant, slow mixing of cosmic ingredients at the boundary. Every measurement from this new phase of the mission served to deepen the mystery and beauty of our place in the galaxy. Voyager was no longer just a runner crossing a finish line. It had become a deep-sea diver, descending slowly into the waters of the galactic ocean, reporting on the pressure, the currents, and the composition of this entirely new environment. Its continued operation, over a decade after its historic crossing, is a testament to human ingenuity and the relentless curiosity that launched it. Each bit of data is precious. Each slight variation in particle count or magnetic field direction, a new piece of a puzzle that is slowly revealing the true nature of the space between the stars. The voyage of discovery did not end in August 2012. It simply changed its name, transitioning from a journey to the edge into an endless exploration of the infinite deep. The confirmation of Voyager 1's passage into interstellar space stands as one of humanity's most profound quiet achievements, a testament to patient inquiry and our enduring desire to comprehend our place within the cosmic vastness. This milestone, reached after 35 years of travel through the dark, represents not an endpoint, but rather a transition into a new and even more subtle phase of exploration, a chapter where every measurement carries the weight of being the first of its kind, the first direct sampling of the galaxy beyond our solar bubble. Having definitively crossed the heliopause, Voyager now serves as our solitary sentinel in the interstellar medium, a robotic ambassador drifting through the galactic currents that surround our tiny stellar island. This environment, known as the local interstellar medium, is far from the static and empty void of popular imagination. Instead, it reveals itself through Voyager's data as a dynamic and complex structure, shaped by immense gravitational forces and gentle plasma flows, a cosmic weather pattern of unimaginable scale that Voyager is now uniquely positioned to characterize. Its continued mission represents the pinnacle of remote sensing, listening to whispers across light years to understand how our solar system interacts with the galaxy at large. Each piece of data returned a precious insight into a region previously known only through theoretical models and distant astronomical observation. The ongoing investigations conducted by Voyager's instruments in this interstellar phase represent some of the most delicate measurements ever attempted in the history of space exploration. The plasma wave instrument, which provided the critical evidence for the crossing through its detection of plasma oscillations, continues to function as a kind of stellar seismometer in the deep dark, detecting subtle vibrations in the interstellar medium that reveal its density and behavior. The method remains elegantly simple in principle, yet breathtakingly complex in execution. When shock waves from solar events, coronal mass ejections that erupted from the sun months or years earlier, propagate across the heliopause and into the interstellar medium, they cause the local plasma to vibrate at specific frequencies determined by the electron density. By analyzing these frequencies with painstaking precision, scientists can calculate this density with remarkable accuracy, each measurement providing a data point in the mapping of our local galactic environment. Over time, these accumulated measurements have revealed a fascinating and unexpected trend. The plasma density has been slowly but steadily increasing as Voyager moves farther from the heliopause and deeper into what astronomers call the local interstellar cloud. This region of slightly enhanced density within the broader galactic environment represents the immediate cosmic neighborhood through which our solar system is traveling. And Voyager's measurements suggest this cloud possesses internal structure and density gradients that were previously undetectable from within our solar bubble. Each new density measurement functions like a depth sounding in an unexplored ocean, revealing the gradual changes in the cosmic waters that surround our solar system and providing crucial data for understanding the pressure balance between the heliosphere and the galaxy beyond. Simultaneously, the magnetometer continues its unending vigil, monitoring the interstellar magnetic field with a sensitivity that belies the instrument's age and the spacecraft's distance from home. The data it returns shows that this magnetic field is not the uniform, placid structure that simpler models might predict, but rather displays subtle variations and fluctuations that speak to the dynamic nature of the interstellar environment. These magnetic perturbations appear to be evidence of turbulence generated by the motion of the heliosphere through the interstellar cloud, a cosmic interaction of staggering scale. As our solar system moves at approximately 52,000 miles per hour relative to the local standard of rest, It creates a kind of bow wave and trailing wake in the interstellar medium, disturbing the magnetic field lines and producing ripples and eddies that Voyager can detect as it moves through this disturbed region. These magnetic fluctuations represent the ghostly imprint of our star's passage through the galaxy, a subtle signature of the solar system's motion through the cosmic medium. And by studying their characteristics, their frequency, amplitude, and direction, scientists can infer properties of the interstellar medium itself that would otherwise remain unknown, such as its dynamic pressure, temperature variations, and flow dynamics around the heliosphere. This information proves crucial for understanding the larger-scale structure of our galactic neighborhood and for refining models of how star systems interact with their environments over astronomical timescales, providing insights that reach far beyond our immediate cosmic vicinity. The cosmic ray detectors aboard Voyager continue their silent census of high-energy particles, providing equally valuable data about the interstellar environment. With the solar wind particles now virtually absent from the measurements, these instruments measure the constant flux of galactic cosmic rays, atomic nuclei accelerated to nearly the speed of light by distant supernovae, active galactic nuclei, and other violent cosmic events across the Milky Way. Voyager's measurements in interstellar space provide something precious, a baseline for cosmic ray intensity completely uncontaminated by solar modulation, a pure view of the galactic particle spectrum that astronomers have long sought to obtain. Interestingly, the data shows a slight but persistent asymmetry, a directional preference, in the arrival of these particles, with cosmic rays tending to stream along the magnetic field lines of the interstellar medium. This directional flow provides further confirmation of the field's orientation and reveals how magnetic structures channel particle flows across the galaxy, creating cosmic highways for high-energy particles. Additionally, Voyager has detected a faint but consistent population of particles that appear to be leaking out from the heliosphere itself. Particles that were once part of the solar wind were accelerated at the termination shock and are now finding pathways to escape into interstellar space. This leakage demonstrates that the heliopause is not an impermeable barrier, but rather a porous interface allowing slow exchange between the solar and galactic environments, a discovery that changes our understanding of how stellar systems interact with their galactic surroundings. The continued operation of Voyager 1 in this interstellar phase represents a remarkable feat of engineering perseverance and scientific dedication. The spacecraft systems are powered by radioisotope thermoelectric generators, which convert the heat from the radioactive decay of plutonium-238 into electricity. As the plutonium decays, the power output gradually declines at a predictable rate of about 4 watts per year, forcing engineers to make increasingly difficult decisions about which instruments to keep active and which to shut down to conserve precious power. Non-essential systems have long been deactivated, including the cameras that captured those iconic images of the planets decades ago, their final frames forever aimed at the receding solar system. Yet the fields and particles instruments, the heart of the interstellar mission, continue to function. Their data transmitted back to Earth via a faint radio signal that now takes over 21 hours to travel across the 14 billion miles that separate Voyager from its creators. The Deep Space Network's massive antennas must listen with exquisite sensitivity to detect this whisper amid the background noise of the universe, a signal so faint that its total power reaching Earth is measured in billionth of a watt. Each day of continued operation represents a triumph of human ingenuity, extending humanity's reach farther into the cosmic ocean and providing insights that will shape our understanding of our galactic neighborhood for generations to come. The spacecraft continues its endless drift, measuring, listening, and recording, a silent witness to the wonders of the interstellar medium, its data stream a gentle lullaby of discovery that lulls us to sleep with visions of cosmic frontiers. The confirmation of Voyager 1's passage into interstellar space stands as one of humanity's most profound quiet achievements, a testament to patient inquiry and our enduring desire to comprehend our place within the cosmic vastness. This milestone, reached after 35 years of travel through the dark, represents not an endpoint, but rather a transition into a new and even more subtle phase of exploration, a chapter where every measurement carries the weight of being the first of its kind, the first direct sampling of the galaxy beyond our solar bubble. Having definitively crossed the heliopause, Voyager now serves as our solitary sentinel in the interstellar medium, a robotic ambassador drifting through the galactic currents that surround our tiny stellar island. This environment, known as the local interstellar medium, is far from the static and empty void of popular imagination. Instead, it reveals itself through Voyager's data as a dynamic and complex structure, shaped by immense gravitational forces and gentle plasma flows, a cosmic weather pattern of unimaginable scale that Voyager is now uniquely positioned to characterize. Its continued mission represents the pinnacle of remote sensing, listening to whispers across light years to understand how our solar system interacts with the galaxy at large. Each piece of data returned a precious insight into a region previously known only through theoretical models and distant astronomical observation. The ongoing investigations conducted by Voyager's instruments in this interstellar phase represent some of the most delicate measurements ever attempted in the history of space exploration. The plasma wave instrument, which provided the critical evidence for the crossing through its detection of plasma oscillations, continues to function as a kind of stellar seismograph in the deep dark, detecting subtle vibrations in the interstellar medium that reveal its density and behavior. The method remains elegantly simple in principle, yet breathtakingly complex in execution. When shock waves from solar events, coronal mass ejections that erupted from the sun months or years earlier, propagate across the heliopause and into the interstellar medium, they cause the local plasma to vibrate at specific frequencies determined by the electron density. By analyzing these frequencies with painstaking precision, scientists can calculate this density with remarkable accuracy, each measurement providing a data point in the mapping of our local galactic environment. Over time, these accumulated measurements have revealed a fascinating and unexpected trend. The plasma density has been slowly but steadily increasing as Voyager moves farther from the heliopause and deeper into what astronomers call the local interstellar cloud. This region of slightly enhanced density within the broader galactic environment represents the immediate cosmic neighborhood through which our solar system is traveling, and Voyager's measurements suggest this cloud possesses internal structure and density gradients that were previously undetectable from within our solar bubble. Each new density measurement functions like a depth sounding in an unexplored ocean, revealing the gradual changes in the cosmic waters that surround our solar system and providing crucial data for understanding the pressure balance between the heliosphere and the galaxy beyond. Simultaneously, the magnetometer continues its unending vigil, monitoring the interstellar magnetic field with a sensitivity that belies the instrument's age and the spacecraft's distance from home. The data it returns shows that this magnetic field is not the uniform, placid structure that simpler models might predict, but rather displays subtle variations and fluctuations that speak to the dynamic nature of the interstellar environment. These magnetic perturbations appear to be evidence of turbulence generated by the motion of the heliosphere through the interstellar cloud, a cosmic interaction of staggering scale. As our solar system moves at approximately 52,000 miles per hour relative to the local standard of rest, it creates a kind of bow wave and trailing wake in the interstellar medium, disturbing the magnetic field lines and producing ripples and eddies that Voyager can detect as it moves through this disturbed region. These magnetic fluctuations represent the ghostly imprint of our star's passage through the galaxy, a subtle signature of the solar system's motion through the cosmic medium. And by studying their characteristics, their frequency, amplitude, and direction, scientists can infer properties of the interstellar medium itself that would otherwise remain unknown, such as its dynamic pressure, temperature variations, and flow dynamics around the heliosphere. This information proves crucial for understanding the larger scale structure of our galactic neighborhood and for refining models of how star systems interact with their environments over astronomical timescales, providing insights that reach far beyond our immediate cosmic vicinity. The cosmic ray detectors aboard Voyager continue their silent census of high-energy particles, providing equally valuable data about the interstellar environment. With the solar wind particles now virtually absent from the measurements, these instruments measure the constant flux of galactic cosmic rays, atomic nuclei accelerated to nearly the speed of light by distant supernovae, active galactic nuclei, and other violent cosmic events across the Milky Way. Voyager's measurements in interstellar space provide something precious, a baseline for cosmic ray intensity completely uncontaminated by solar modulation, a pure view of the galactic particle spectrum that astronomers have long sought to obtain. Interestingly, the data shows a slight but persistent anisotropy, a directional preference, in the arrival of these particles, with cosmic rays tending to stream along the magnetic field lines of the interstellar medium. This directional flow provides further confirmation of the field's orientation and reveals how magnetic structures channel particle flows across the galaxy, creating cosmic highways for high-energy particles. Additionally, Voyager has detected a faint but consistent population of particles that appear to be leaking out of the heliosphere itself. Particles that were once part of the solar wind were accelerated at the termination shock and are now finding pathways to escape into interstellar space. This leakage demonstrates that the heliopause is not an impermeable barrier, but rather a porous interface allowing slow exchange between the solar and galactic environments, a discovery that changes our understanding of how stellar systems interact with their galactic surroundings. The continued operation of Voyager 1 in this interstellar phase represents a remarkable feat of engineering perseverance and scientific dedication. The spacecraft's systems are powered by radioisotope thermoelectric generators, which convert the heat from the radioactive decay of plutonium-238 into electricity. As the plutonium decays, the power output gradually declines at a predictable rate of about 4 watts per year, forcing engineers to make increasingly difficult decisions about which instruments to keep active and which to shut down to conserve precious power. Non-essential systems have long been deactivated, including the cameras that captured those iconic images of the planets decades ago, their final frames forever aimed at the receding solar system. Yet the fields and particles instruments, the heart of the interstellar mission, continue to function, their data transmitted back to Earth via a faint radio signal that now takes over 21 hours to travel across the 14 billion miles that separate Voyager from its creators. The Deep Space Network's massive antennas must listen with exquisite sensitivity to detect this whisper amid the background noise of the universe, a signal so faint that its total power reaching Earth is measured in billionths of a watt. Each day of continued operation represents a triumph of human ingenuity, extending humanity's reach farther into the cosmic ocean and providing insights that will shape our understanding of our galactic neighborhood for generations to come. The spacecraft continues its endless drift, measuring, listening, and recording, a silent witness to the wonders of the interstellar medium, its data stream a gentle lullaby of discovery that lulls us to sleep with visions of cosmic frontiers. As Voyager 1 continues its endless journey, moving ever deeper into the galactic ocean, its mission transforms from one of pure discovery to one of profound monitoring. It has become a stationary buoy in the cosmic sea, anchored not by chain, but by inertia, its sensors attuned to the slow, grand rhythms of the galaxy. The questions it now seeks to answer are no longer about where it is, but about what surrounds it, the very nature of the space between the stars. This phase of the mission is perhaps the most serene, a long, quiet observation of a realm we once thought was featureless and still, but which Voyager has revealed to be rich with subtle activity and unseen structure. The spacecraft's ongoing measurements of the interstellar plasma density have yielded one of the most significant and unexpected discoveries of this late phase. The initial readings taken after crossing the heliopause in 2012 showed a density of approximately 0.08 electrons per cubic centimeter. This was already 40 times denser than the solar wind plasma in the outer heliosheath, confirming the crossing. But as the years passed and more solar shocks arrived to make the plasma ring, scientists noticed a clear and persistent trend. The density was increasing. With each subsequent measurement, the number climbed higher. By 2018, densities had risen to nearly 0.13 electrons per cubic centimeter, and later measurements suggested a continued slow climb. This was a revelation. It provided the first ever direct evidence that our solar system is moving through a distinct region of space known as the local interstellar cloud. This cloud, also called the local fluff, is a region of slightly denser and warmer material within a much larger, emptier void known as the local bubble, which was carved out by ancient supernova explosions millions of years ago. Voyager is not sailing through a uniform, homogeneous medium. It is traversing a specific cloud with its own boundaries and internal structure. The increasing density measurements suggest that Voyager is moving deeper into the heart of this cloud, mapping its gradient for the very first time. Each new plasma oscillation event is like taking a core sample from this galactic environment, building a profile of our local neighborhood and revealing that interstellar space has its own geography, its own hills and valleys of density and pressure that were entirely unknown before Voyager's direct sampling. Simultaneously, the magnetometer continues to trace the invisible architecture of the local interstellar magnetic field. The data reveals this field to be surprisingly strong and remarkably stable in its direction, but far from smooth. It is etched with fine-scale variations, a gentle turbulence that speaks of dynamic processes at work. Scientists now understand these fluctuations as the magnetic wake of our solar system. As the heliosphere plows through the local interstellar cloud at over 50,000 miles per hour, it does not move through a passive fluid. It interacts with it, compressing the galactic magnetic field directly ahead of it and stretching it into a long, turbulent wake behind it, much like the wake of a ship moving through water. Voyager, having exited the heliosphere on its northern flank, is now traveling through this disturbed region, this magnetic wake. The subtle ripples and eddies it detects in the field are the ghostly signatures of our star's motion through the galaxy, a cosmic fingerprint left on the interstellar medium. By studying this magnetic turbulence, scientists can infer properties that are impossible to measure directly, such as the speed and direction of the flow of interstellar material around the heliosphere, and the total pressure this environment exerts on our solar bubble. The cosmic ray instruments, too, continue their silent census, but now with a new focus. With the solar particles gone, their primary role is to monitor the pure, unmodulated flux of galactic cosmic rays. However, they have also detected a second, much smaller population of particles that tell a fascinating story of exchange. These are the so-called energetic neutral atoms. This process begins inside the heliosheath, where hot solar wind particles interact with cold neutral atoms that have drifted in from the interstellar medium. During a collision, a charged solar wind proton can steal an electron from a neutral interstellar atom. This charge exchange transforms the proton into a neutral hydrogen atom. Being neutral, it is no longer tied to the magnetic fields of the heliosphere. It flies off in a straight line, and a fraction of these particles fly right back out into interstellar space, where Voyager can detect them. The presence of these particles is profound. It means that material from inside our solar system is finding a way to escape and mix with the galactic environment. It is a form of leakage, a slow exhalation of our solar system's substance into the galaxy. Conversely, neutral atoms from the galaxy constantly drift inward, past Voyager, toward the sun, where they will eventually undergo the reverse process and become part of the solar wind. This two-way exchange demonstrates that the heliopause is not a solid, impermeable wall, but a complex and dynamic membrane through which the cosmos and our solar system are in a constant, slow-motion dialogue. Voyager is situated at the perfect point to listen to both sides of this conversation, measuring what flows out and inferring what flows in. The operation of the spacecraft itself has become a delicate and increasingly challenging ballet of power management. The relentless decay of the plutonium-238 and its RTGs means that every year, Voyager has approximately 4 fewer watts of power with which to operate. The team on Earth has had to make difficult, calculated decisions to keep the core fields and particles instruments alive. Heaters have been turned off, one by one, relying on the increasingly deep cold of space to keep certain components functional. Systems are run on ever thinner margins. Yet through brilliant and frugal engineering, the essential instruments continue to function. The data that streams back is a trickle of ones and zeros, a digital whisper that is the culmination of over 4 decades of journeying. It is gathered by the immense, sensitive ears of the Deep Space Network, radio telescopes in California, Spain, and Australia that take turns listening to the faint signal as the Earth rotates. Catching each bit of data is an act of faith and precision, a testament to our species' unwavering desire to reach out and understand, to keep listening even as the voice from the dark grows ever fainter. Voyager's journey is a continuous process of redefining the edge. It has shown us that the boundary of our solar system is not a line but a zone, not an end but a beginning. It is a region of interaction, of mixing, of complex and beautiful physics that governs how a star lives within its galactic ecosystem. Every new data point returned is a permanent addition to human knowledge, a detail in the first ever map of the interstellar medium, drawn not by distant observation, but by direct touch. The spacecraft sails on, a silent, steadfast witness to the gentle currents of the galaxy, its ongoing mission a quiet lullaby of discovery, soothing us with the profound truth that we have, in a very real sense, touched the stars. As Voyager 1's journey extends from years into decades within the interstellar medium, its role evolves from that of a pathfinder to a foundational observatory. The data it returns is no longer merely about confirming its location, but about building the first long-term baseline of the galactic environment. This is a critical distinction. Before Voyager, our understanding of the space between stars was theoretical, based on snapshots from astronomy. Voyager provides a continuous, in situ record, revealing how this environment changes over time, a timescale of years and decades, which is a mere blink in cosmic terms, but a revolutionary data set for humanity. It is the difference between seeing a single frame of the ocean and measuring its tides, currents, and temperature variations over many seasons. One of the most captivating ongoing investigations involves listening for the faintest echoes of the sun's past activity. The plasma wave instrument, so crucial to the crossing discovery, now acts as a historian of solar storms. When a large coronal mass ejection erupts from the sun, it creates a pressure wave that propagates outward in all directions. Months or even over a year later, this wave finally reaches Voyager's location in interstellar space. When it passes through, it compresses the local interstellar plasma, causing it to oscillate at that characteristic low frequency. The PWS records this ringing, and scientists can not only measure the density from the tone, but also study the structure of the shock wave itself. By analyzing how these shocks evolve and weaken as they travel billions of miles beyond the planets, scientists gain new insights into the physics of shock propagation and the energy transfer between the sun and the galaxy. Every detected event is like finding a bottled message that was launched from the sun over a year prior, its contents revealing secrets about the storm's power and the nature of the medium it has traveled through. Simultaneously, the magnetometer's unending data stream is meticulously searched for signs of the largest scale structures in our galactic neighborhood. A primary goal is to detect evidence of the hypothesized hydrogen wall, a theorized accumulation of neutral hydrogen gas that may be piling up just outside the heliopause due to the pressure of the interstellar wind against the solar bubble. The magnetic signature of such a structure would be subtle, a slight enhancement or deflection in the field lines, but its detection would provide a crucial missing piece in the model of how the heliosphere interacts with the surrounding cloud of. Furthermore, by monitoring the magnetic field's long-term stability and its subtle fluctuations, Voyager helps scientists understand the pressure equilibrium that defines the very size and shape of our solar system's protective bubble. The data suggests the heliosphere may be more compact and dynamic than previously believed, shaped not just by the solar wind, but also by the powerful confines of the local interstellar magnetic field through which it moves. The cosmic ray detectors continue to tell a story of connection to the broader galaxy. The steady flux of galactic cosmic rays is now the background norm, but it is not perfectly constant. Voyager has observed slight, gradual increases in this radiation over time. This is not yet fully understood, but one compelling theory suggests it could be a sign that the heliosphere itself is moving through a region of space with a slightly higher cosmic ray density. Or perhaps even that the sun's protective magnetic bubble is undergoing long-term cycles of compression and expansion, subtly modulating how much of this galactic radiation can reach its inner edge. Voyager, now outside the bubble, measures the true, unfiltered source, providing the baseline against which all measurements made inside the solar system must be compared. It is the control experiment for understanding how our star shields its planetary system. Yet, even as it forges ahead into new scientific territory, the inevitable, gentle decline of the mission continues. The power output from the RTGs continues its slow, inexorable decrease. The engineering team on Earth, a small group of dedicated stewards for this legacy project, has entered a final, carefully managed phase of power conservation. Their strategy is no longer about prioritizing one science instrument over another, but about shutting down redundant systems and safety heaters to keep the single most critical fields and particles package alive for as long as possible. They have commanded the spacecraft to use its precious remaining power to operate its instruments in a clever, pulsed mode, turning them on for specific intervals to capture data before powering them down again to conserve energy. Every command sent to Voyager is a calculated risk, a meticulously crafted sequence of instructions that must travel for over 21 hours at the speed of light to reach it. There is no real-time control anymore. The team can only listen and hope their commands were received and executed correctly. The signal returning to Earth is now almost unimaginably faint, a whisper of a whisper. The Deep Space Network must use its most advanced signal processing techniques, combining the data from multiple large antennas to tease the precious science data out of the background radio noise of the universe itself. The daily download from Voyager is a trickle of data, a few hundred bits per second, but each bit is a priceless nugget of information from a realm we will not visit again for generations. And so, the mission continues its slow, quiet fade. There is no dramatic finale planned, no grand shutdown. The end will be as serene as the journey itself. One day, perhaps in the mid-2020s, the power will simply become too low to operate any scientific instrument. The heaters that keep the fuel mines from freezing will finally shut down. Soon after, the radio transmitter itself will fall silent. Voyager 1 will not know it has died. It will simply continue on, its internal systems freezing one by one in the absolute zero cold of interstellar space. It will become a silent, inert artifact, a fossil of human ingenuity. But its journey will be far from over. It will sail on, forever drifting along its timeless trajectory, carrying its golden record into the cosmic future. A permanent testament to the quiet, curious species that once, from a distant pale blue dot, reached out and touched the galaxy. The story of Voyager 1 is, in its final analysis, not merely a tale of engineering triumph or scientific discovery, but a profound meditation on time, memory, and the human spirit's relentless pursuit of meaning in the vast and silent cosmos. As the spacecraft's power fades and its final transmissions are received on Earth, its mission transitions from one of active measurement to one of passive legacy. It becomes a monument, not of stone or metal, but of intention, hurled into the future. Its enduring value shifts from the data it streams back to the simple, staggering fact of its existence, a human-made object enduring in the interstellar dark, a permanent bookmark in the library of the galaxy. This transition invites a deeper reflection on the nature of exploration itself. For centuries, exploration meant sending people to new lands to see, to touch, and to map, and to return with tales of what they had witnessed. Voyager redefines this concept entirely. It is exploration by proxy, by sensation. We cannot see where it is. We cannot send a camera to photograph the interstellar medium. Instead, we must feel our way into this new realm, using the spacecraft's instruments as our fingertips in the dark. We explore through the language of physics, through fluctuations in magnetic field strength, through oscillations in plasma density, through the counting of subatomic particles. This is a purer, more abstract form of discovery, one that requires us to translate numerical data into a mental image of a place we will never visually perceive. It is a testament to the power of the human mind to comprehend environments far beyond the limits of our biological senses. The golden record attached to Voyager's side embodies this philosophical weight. While its primary purpose is a message to any potential finder, its deeper function may be as a message to ourselves. It is a cultural time capsule, a deliberate act of self-reflection forced upon us by the mission. To decide what to send to the stars is to ask the most fundamental questions about our species. Who are we? What is important to us? What defines our planet? The images of landscapes, the diagrams of DNA, the recordings of greetings in countless languages, the brainwaves of a woman in love, the sounds of crickets and thunderstorms. This collection is not a comprehensive database of human knowledge. It is a poem. It is a carefully curated selection of moments and concepts that we, at our best, hope define us. Our curiosity, our artistry, our diversity, our connection to our world, and our yearning to connect with others. The record transforms Voyager from a mere probe into a story. It is the narrative we have chosen to tell about ourselves, cast adrift in the hope that a listener might one day understand its verses. And yet the most likely future for Voyager is one of profound and endless solitude. The scale of interstellar space renders the probability of an encounter with another intelligence infinitesimally small. The spacecraft will, in all likelihood, never be found. It will sail on for eons through the silent, empty vastness between the stars. Its destiny is to become a relic of a civilization that may itself one day be gone, a silent witness to the life and death of stars, the slow dance of galaxies, and the unfathomable stretches of cosmic time. It will outlive the pyramids, outlive every human structure, outlive even the continents of Earth. It is the most durable artifact our species has ever created, its journey measured not in centuries, but in billions of years. This brings us to the final, quiet act of the mission, the silence. The gradual power decline is not a failure, it is the natural and expected conclusion to this decades-long conversation. The team of engineers and scientists on Earth, the stewards of the stream, know that each command they send could be the last one that is successfully received. Each day of data is a gift. The moment the signal finally ceases will be a moment of deep poignancy, but not of tragedy. It will be the closing of a chapter, the gentle end of an active dialogue that began in the 1970s. The people who will be on duty to witness the final loss of signal were not yet born when Voyager was launched. They are the inheritors of a legacy, the last listeners in a chain of generations that have tended this tiny whisper from the edge. When the signal stops, Voyager will not be dead. It will be free. Its mission of communication will be complete, and its deeper mission of endurance will truly begin. It will become a permanent citizen of the Milky Way galaxy, orbiting its center long after the sun has cooled and died. It will carry our story, our poem, our record of a watery world teeming with life and wonder into a future we cannot imagine. So, as you drift towards sleep, consider this. The knowledge of Voyager's journey changes our relationship with the universe. We can look up at the night sky, not as a distant and unreachable canvas of pinpricks of light, but as an ocean that we have touched. We know that out there, in the quiet between the stars, a piece of our humanity sails on. It is a thought that is simultaneously humbling and empowering. It reminds us of our smallness in the cosmos, but also of the breathtaking grandeur of our curiosity. The question we began with, how do we know, has been answered, not with a simple declaration, but with a long, patient, and beautiful story of inference, measurement, and wonder. It is a story that continues even now in the faint, steady whisper of data from the edge, a lullaby of science that reminds us we have, quietly and methodically, begun to make the cosmos our home. While Voyager 1 journeys through the silent, sunless expanse of interstellar space, its story is inextricably tethered to a small, dedicated community on Earth. The narrative of this mission is not just one of metal and circuitry in the void. It is a profoundly human story, a decades-long vigil maintained by scientists and engineers who have devoted their careers to listening. This is the ground segment of the dream, the quiet, unglamorous work of tending to a conversation where every word takes over 21 hours to arrive. For them, Voyager is not a relic of the past, but a living, breathing mission, its heartbeat measured in the faint, rhythmic pulse of its carrier signal locked in by the giant antennas of the Deep Space Network. The team that tends to Voyager today is a fraction of the size of the Legion that launched it. They are not the original engineers, but their successors, sons and daughters of the space age, who inherited the manuals, the software, and the profound responsibility of shepherding this artifact into its final years. Theirs is a unique form of archaeology. They must maintain expertise in 1970s-era technology, often reverse engineering the logic of their predecessors from notes and diagrams, while simultaneously pushing the boundaries of modern data analysis to extract new secrets from the aging data stream. They speak of the spacecraft not as a machine, but with a kind of affection and familiarity, knowing its every quirk and idiosyncrasy. They understand its tolerances, its aging systems, its stubborn refusal to quit. This intimate knowledge is crucial, for every command sent is an irreversible act. There are no quick fixes, no service missions. Every decision must be perfect, calculated months in advance, its consequences considered across billions of miles. The primary challenge of this late phase is power management, a slow and meticulous exercise in triage. The radioactive decay of the plutonium-238 in the RTGs is immutable and unforgiving. The power output drops by about 4 watts each year. The team has already shut down the heaters for most instruments, relying on the ever-deepening cold of space to keep components within survivable limits, a calculated gamble that, astonishingly, has paid off. Non-essential systems were deactivated long ago. The famous cameras, their final portraits of the solar system captured decades ago, are frozen and silent. The team's focus is now on the heart of the mission, the suite of fields and particles instruments. The strategy is one of shared sacrifice. To keep one instrument alive for another year, another may have to be powered down sooner. They operate on a knife's edge, squeezing every last joule of energy from the fading generators, constantly developing new, more efficient software patches to minimize power consumption during data collection and transmission. And then there is the challenge of the signal itself. The radio transmissions from Voyager, already weak at the planetary encounters, are now almost vanishingly faint. By the time they reach Earth, the power of the signal is measured in fractions of a billionth of a watt. To detect this whisper, the Deep Space Network employs its largest 70-meter-wide antennas using incredibly sensitive receivers cooled to near absolute zero to minimize internal noise. Even then, the data rate is agonizingly slow, a trickle of 160 bits per second, a pace slower than the dial-up modems of the 1980s. To compensate, the team uses immense patience. They carefully schedule listening sessions, sometimes combining the power of multiple antennas to boost the signal, and employ sophisticated error-correcting codes to ensure that every precious bit of data is recovered accurately. Downloading a single day's worth of measurements can take hours. This is not the fast-paced, high-bandwidth world of modern missions. It is a slow, meditative process of accumulation, of building a picture of the interstellar medium one painstaking pixel at a time. Yet within this slow stream of data lies continuous discovery. The team's work is far from mere maintenance. It is active, frontier science. Every week, they analyze the latest readings from the magnetometer, looking for subtle shifts that might indicate a new feature in the interstellar magnetic field. They eagerly await the next solar shock wave, knowing it will trigger the plasma wave instrument and provide another crucial measurement of the increasing density of the local interstellar cloud. They monitor the cosmic ray data for any anomalies, any hints of new phenomena at the boundary between the stellar and the galactic. For these scientists, the Voyager mission is the ultimate long-term study. They are the first humans to directly monitor the weather of interstellar space over a period of years, and each new data point adds to a graph that is utterly unique in history. This long vigil is a testament to a different kind of exploration ethos, one not of brief flags and footprints, but of permanent presence and patient understanding. It is a promise kept across generations, a statement that our curiosity does not end at the planetary frontier. The men and women who listen for Voyager's whisper are the keepers of that promise. They work in quiet rooms, staring at screens of scrolling numbers, their eyes and ears trained to detect meaning in the faintest of signals. They may never make headlines, but they are arguably humanity's most far-reaching sensory organs, interpreting the touch of the galactic current on a sensor array 14 billion miles away. Their daily work is the quiet, methodical answer to the question of how we know Voyager is there. We know because they are still listening with a patience and dedication that is, in its own way, as vast as the space the spacecraft now calls home. While Voyager 1 journeys through the silent, sunless expanse of interstellar space, its story is inextricably tethered to a small, dedicated community on Earth. The narrative of this mission is not just one of metal and circuitry in the void. It is a profoundly human story, a decades-long vigil maintained by scientists and engineers who have devoted their careers to listening. This is the ground segment of the dream, the quiet, unglamorous work of tending to a conversation where every word takes over 21 hours to arrive. For them, Voyager is not a relic of the past, but a living, breathing mission, its heartbeat measured in the faint, rhythmic pulse of its carrier signal, locked in by the giant antennas of the Deep Space Network. The team that tends to Voyager today is a fraction of the size of the Legion that launched it. They are not the original engineers, but their successors, sons and daughters of the space age who inherited the manuals, the software, and the profound responsibility of shepherding this artifact into its final years. Theirs is a unique form of archaeology. They must maintain expertise in 1970s-era technology, often reverse engineering the logic of their predecessors from notes and diagrams, while simultaneously pushing the boundaries of modern data analysis to extract new secrets from the aging data stream. They speak of the spacecraft not as a machine, but with a kind of affection and familiarity, knowing its every quirk and idiosyncrasy. They understand its tolerances, its aging systems, its stubborn refusal to quit. This intimate knowledge is crucial, for every command sent is an irreversible act. There are no quick fixes, no service missions. Every decision must be perfect, calculated months in advance, its consequences considered across billions of miles. The primary challenge of this late phase is power management, a slow, meticulous exercise in triage. The radioactive decay of the plutonium-238 in the RTGs is immutable and unforgiving. The power output drops by about 4 watts each year. The team has already shut down the heaters for most instruments, relying on the ever-deepening cold of space to keep components within survivable limits. A calculated gamble that has, astonishingly, paid off. Non-essential systems were deactivated long ago. The famous cameras, their final portraits of the solar system, captured decades ago, are frozen and silent. The team's focus is now on the heart of the mission, the suite of fields and particles instruments. The strategy is one of shared sacrifice. To keep one instrument alive for another year, another may have to be powered down sooner. They operate on a knife's edge, squeezing every last joule of energy from the fading generators, constantly developing new, more efficient software patches to minimize power consumption during data collection and transmission. And then there is the challenge of the signal itself. The radio transmissions from Voyager, already weak at the planetary encounters, are now almost vanishingly faint. By the time they reach Earth, the power of the signal is measured in fractions of a billionth of a watt. To detect this whisper, the Deep Space Network employs its largest 70-meter-wide antennas, using incredibly sensitive receivers cooled to near absolute zero to minimize internal noise. Even then, the data rate is agonizingly slow, a trickle of 160 bits per second, a pace slower than the dial-up modems of the 1980s. To compensate, the team uses immense patience. They carefully schedule listening sessions, sometimes combining the power of multiple antennas to boost the signal, and employ sophisticated error-correcting codes to ensure that every precious bit of data is recovered accurately. Downloading a single day's worth of measurements can take hours. This is not the fast-paced, high-bandwidth world of modern missions. It is a slow, meditative process of accumulation, of building a picture of the interstellar medium one painstaking pixel at a time. They monitor the cosmic ray data for any anomalies, any hints of new phenomena at the boundary between the stellar and the galactic. For these scientists, the Voyager mission is the ultimate long-term study. They are the first humans to directly monitor the weather of interstellar space over a period of years, and each new data point adds to a graph that is utterly unique in history. This long vigil is a testament to a different kind of exploration ethos, one not of brief flags and footprints, but of permanent presence and patient understanding. It is a promise kept across generations, a statement that our curiosity does not end at the planetary frontier. The men and women who listen for Voyager's whisper are the keepers of that promise. They work in quiet rooms, staring at screens of scrolling numbers, their eyes and ears trained to detect meaning in the faintest of signals. They may never make headlines, but they are arguably humanity's most far-reaching sensory organs, interpreting the touch of the galactic current on a sensor array 14 billion miles away. Their daily work is the quiet, methodical answer to the question of how we know Voyager is there. We know because they are still listening, with a patience and dedication that is in its own way as vast as the space the spacecraft now calls home. The ongoing saga of Voyager 1 is not merely a countdown to silence. It is a race against time to gather every last precious secret from the interstellar medium before the power fades entirely. The current phase of the mission is one of focused intensity, a period where the scientific return, bit by precious bit, is arguably more valuable than ever because it is irreplaceable. Each day of operation is a gift, and the team on Earth is engaged in a delicate ballet to maximize the yield from this final harvest of data from the frontier. The primary scientific focus now is on long-term monitoring. The initial crossing of the heliopause was a monumental event, but it was a single data point in time. The true value lies in understanding how this dynamic boundary breathes and changes. The solar cycle continues on its 11-year rhythm, and even from across the heliosphere, Voyager feels its effects. Periods of high solar activity generate more powerful solar winds and more frequent coronal mass ejections. Years later, the shock waves from these events finally reach Voyager, compressing the local interstellar medium and causing the plasma to ring. Each new ringing event provides a fresh measurement of the plasma density, allowing scientists to track its changes over time. This is no longer about a single confirmation. It is about creating a timeline, a history of the density fluctuations in our local galactic environment. Is the density increasing steadily as we move through the local interstellar cloud? Does it vary with the sun's activity? These are questions only Voyager can answer, and each new plasma wave detection adds a crucial point to the graph. Simultaneously, the magnetometer continues its endless vigil. The team is searching for subtle, long-term trends in the direction and strength of the interstellar magnetic field. The theory of magnetic draping suggests that the field lines of the interstellar medium are pulled and stretched around the heliosphere as it moves. Voyager's data is the key to testing this model. By analyzing tiny, gradual shifts in the field over months and years, scientists can map the large-scale structure of this draped magnetic field, inferring the shape and pressure of the heliosphere from the outside, a view we have never had before. This isn't about a sudden flip. It's about detecting the incredibly slow and subtle curvature of the galactic magnetic fabric as it flows around our solar system. The cosmic ray detectors are also busy with a new mystery. Having established the baseline level of galactic cosmic rays, scientists now watch for deviations. They have observed curious, slow-moving tsunamis of cosmic rays, periodic increases and decreases that propagate through the interstellar medium. The origin of these waves is still debated. They could be echoes of ancient supernovae elsewhere in the galaxy, or they could be generated by the interaction of the heliosphere with the interstellar wind. By monitoring their frequency and intensity, Voyager acts as a seismometer for the galaxy, feeling the rumble of distant cataclysmic events and the gentle pressure waves created by our own star's motion. The engineering effort to support this science is more innovative than ever. With power critically low, the team has developed new, ultra-efficient operating modes. They may power on a single instrument for a short, precise measurement, then power it down completely before reactivating another. They use the spacecraft's minimal thruster pulses not for course changes, its trajectory is forever fixed, but for tiny attitude adjustments to better point its sensors or to improve the alignment of its antenna towards Earth, squeezing out every last decibel of signal strength. Every command sequence is a masterpiece of optimization, designed to extract maximum science from minimum power. This is not an ending. This is the pinnacle of the mission. The questions being asked now are more sophisticated than ever before, built upon the foundational knowledge of the crossing. Voyager is no longer just saying, "I am here." It is now describing in intricate detail what here is like over time. It is characterizing the climate of our galactic neighborhood. The faint signal reaching Earth, though slow, carries within it the first long-term weather report from interstellar space. The journey continues. The data keeps flowing. The quiet vigil of listening and discovery remains unbroken. Let us stay here a while longer, in this moment of active, ongoing exploration, and appreciate the steady stream of whispers from the void. each one telling us more about the cosmic ocean we now know we are a part of. As Voyager 1 continues its solitary traverse through the local interstellar cloud, its value has shifted from making singular, monumental discoveries to detecting and interpreting the faint, background rhythms of the galaxy itself. It has become a listening post, a remote observatory tuned to the lowest frequencies of cosmic weather. The questions it now seeks to answer are about the dynamics of this new environment, its stability, its turbulence, and its interaction with the final, fading echoes of the sun's influence. This is the science of nuance, of trends measured over years, of whispers within the whisper. One of the most critical and ongoing investigations involves the precise monitoring of what scientists call interstellar turbulence. The magnetometer data, once analyzed for the dramatic shift at the heliopause, is now scrutinized for much finer details. The interstellar magnetic field is not a perfectly smooth and uniform structure. It is roiled by subtle waves and ripples, much like the surface of a pond disturbed by a light wind. Voyager is measuring this turbulence directly for the first time. The source of these ripples is a key question. Some are likely generated by the movement of the heliosphere itself through the interstellar medium, its bow wave creating a magnetic wake that Voyager is now sailing through. Others might be the faint propagated echoes of much larger events elsewhere in the galaxy, perhaps shock waves from ancient supernovae that have traveled for millions of years before reaching our local neighborhood. By analyzing the spectrum of this turbulence, the size and frequency of these magnetic ripples, scientists can learn fundamental properties of the interstellar plasma, such as its viscosity and energy dissipation, properties that are crucial for understanding the large-scale dynamics of our galaxy, but were previously only theoretical. Alongside this, the cosmic ray detectors are engaged in a fascinating form of particle archaeology. The constant rain of galactic cosmic rays upon Voyager is not perfectly uniform. Within this rain are different species of particles, protons, helium nuclei, and heavier elements, each with a slightly different energy signature. The precise mix and ratio of these particles act as a fingerprint, revealing their origin and history. Particles that have traveled longer paths through the magnetic fields of the galaxy tend to lose energy and interact in ways that change their composition. By conducting a long-term census of these particles, Voyager is helping to map the structure of the magnetic fields within the local interstellar cloud and beyond. It is providing ground truth data for models that describe how our galactic neighborhood formed and evolved. Every month of additional data allows for more precise measurements of these subtle variations, turning a snapshot into a high-resolution movie of particle flow in the galaxy. Furthermore, Voyager is now detecting the faintest conceivable hint of the sun's presence, a trickle of particles leaking back into the interstellar medium. These are not the solar wind particles it left behind at the heliopause. This is a more subtle process. Inside the heliosheath, energetic particles from the solar wind can interact with neutral atoms drifting in from interstellar space. During these collisions, they can exchange charge, becoming neutral themselves. As neutral atoms, they are no longer constrained by magnetic fields. They zip away in straight lines, and a tiny fraction of them zip right back out past the heliopause, where Voyager can detect them. This faint signal is incredibly valuable. It is direct evidence that the heliopause is not a solid wall, but a porous membrane, allowing for a slow, complex exchange of material between the solar system and the galaxy. Monitoring the intensity of this leak provides clues about the conditions just inside the heliopause, a region Voyager can no longer directly sample, but whose state affects the entire heliosphere. The engineering required to capture this data is a masterpiece of frugality. The team now operates the spacecraft in a power-sharing mode. It is no longer about choosing which instrument to turn on, but about carefully scheduling which subsystems can be powered down, and for how long, to bank enough energy for a specific short-duration observation with a single sensor. They might disable a heater for a few days to accumulate enough power to run the plasma wave instrument for a crucial few hours when a long-awaited solar shock wave is predicted to arrive. This requires an intimate, almost symbiotic knowledge of the spacecraft's capabilities and the scientific goals. It is a continuous, carefully calculated gamble, pushing the spacecraft to its absolute limits to pry loose one more secret from the interstellar medium. This is the current reality of the mission, not a farewell, but an intense and focused collaboration between human ingenuity on Earth and a resilient machine in the void. The signal is still there, however faint. The data is still flowing, however slowly. Each new piece of information is a stroke on a canvas that is still largely blank, the first ever painting of the interstellar environment in real time. The journey of discovery is as active today as it was a decade ago. The questions have simply become more refined, the answers more subtle. The quiet conversation across the billions of miles continues, a testament to the enduring power of a simple, profound question: what is next? We began our voyage with a single, profound question. How can we be certain that a silent speck of technology, launched a lifetime ago and now vanished from our sight, has truly crossed the threshold into the space between the stars? The answer, as we have gently unpacked, is not found in a single triumphant signal, but in a symphony of evidence, a convergence of data from multiple instruments, each telling a part of the story. Their harmony is revealing a truth far greater than any one could alone. We know because of the particles, the permanent and utter disappearance of the solar wind, that relentless outward breath of our sun that had been Voyager's constant companion for decades, and its replacement by an intense, unwavering torrent of galactic cosmic rays, ancient particles accelerated by distant supernovae. This was the first clear chorus in the symphony, a fundamental change in the very substance of the environment. We know because of the magnetic field, the magnetometer's detection of a strengthened field with a subtle but definitive shift in orientation, confirming that the magnetic architecture surrounding the spacecraft was no longer shaped solely by the sun, but was now under the dominion of the galaxy's own immense magnetic web. This was the base note, the deep structural proof that confirmed the particle data. And, most elegantly, we know because of the ring of plasma, the waiting for a solar storm to travel the unthinkable distance and strike the interstellar plasma like a bell, allowing the plasma wave instrument to measure its tone, a deep, low frequency that unequivocally revealed a density 40 times greater than the solar wind. This was the resonant chord that settled the debate, the direct measurement that silenced all remaining doubt. August 25th, 2012 was the day humanity arrived in the galactic ocean. But this crossing was not an end. It was a magnificent beginning. Voyager's ongoing mission has revealed that interstellar space is not an empty, static void. It is a dynamic realm, a place with weather, where the density of the local interstellar cloud slowly increases, where magnetic turbulence ripples from the heliosphere's motion, and where faint tsunamis of cosmic rays wash through. It is a place of exchange, where particles from our sun slowly leak out into the galaxy and galactic material filters in. Voyager has transformed this vast, theoretical emptiness into a place we can characterize, measure, and begin to understand. This knowledge is a testament to a unique blend of human virtues, the bold vision to launch such a mission, the patient dedication to tend to it for over 4 decades, and the brilliant ingenuity to interpret its whispers. It is a story of generations, of those who built it, those who launched it, and those who now, having inherited it, perform the delicate ballet of power management to keep its senses alive in the freezing dark. It is a story that argues for the profound value of pure curiosity, of seeking knowledge not for immediate gain, but for the simple, majestic reason that we are a species that looks at the stars and needs to know what lies there. And soon, the final command will be sent, and the last trickle of power will fade. The faint whisper of data that has been a constant for nearly half a century will finally fall silent. But in that silence, Voyager's purpose will achieve its ultimate transformation. It will transition from a scientific probe to a permanent legacy. It will become a time capsule, a celestial monument carrying the golden record, a story of our world, a song of our existence into the unimaginable future. So, as you drift towards sleep, let the certainty of this journey settle upon you. We know Voyager is there because we listened with patience and understood with wisdom. Its silent, endless drift is no longer a mystery, but a comfort. It is our ambassador to the cosmos, a permanent part of humanity that now belongs to the galaxy. It is proof that we reached beyond our cradle, touched the void, and left a gentle, indelible mark upon it. The story of Voyager is the story of how we know. It is the story of how we touched the infinite. And it is a lullaby reminding us that even in the deepest silence, the echo of our curiosity endures forever. Good night, Space Explorer. Sleep well, and we will meet again in our next journey.